Hello, good day to you all. I'm Chatura Ranganath and I'm one of the corresponding authors of this research, remotely operated rotary inverted pendulum system for online control engineering education. The other co-authors of this research are Mr. Ritna Ganganath and Mr. Buddhika Annaswatha. I'm a former undergraduate student of the University of Wolverhampton, UK, and I'm honored, also excited to present our research findings at this third International Conference on Electrical Engineering and Informatics 2022. As we all are aware, COVID-19 crisis has had an unprecedented impact towards the academia. The education of more than 90% of students globally was disrupted by institutional closures. When the pandemic struck, the educational sector was not exactly prepared and also had to look for immediate solutions. As an ultimate result of the incredible pandemic, physical classroom education has changed rapidly. In the same time, e-learning became the only preferred option for the educational sector. Because of this situation, even in the control engineering courses, all lab practical sessions were massively affected around the world. In this paper, we propose an experiment regarding the rotary inverted pendulum simulation platform, which can be used as an online web-based teaching aid to overcome this issue. This proposed simulator can be utilized as a control engineering online teaching tool, which can support the model-based control system practical sessions. This rotary inverted pendulum system is a platform that is used to perform a wide range of balance control experiments. It is an important nonlinear problem, and the knowledge gained by studying inverted pendulum can be widely used in many control applications. Balance control of an inverted pendulum using the rotary motion in a simulation environment was discussed in this research, and the feasibility of performing these tests in a remote computer setting for a distance learning purposes was tested. This inverted pendulum is the principle that has been using in various kinds of balance control applications such as balancing robots, space applications, leg robots, additive control, and so on. In this study, we used the Euler-Lagrange method to derive the nonlinear equations of motion. With the generalized coordinates, we obtained the Euler-Lagrange equations for the rotary inverted pendulum system, as you can see here in the first two sets of equations. Once the kinetic and potential energy of the system was found and the Lagrangian is obtained, we linearize the system equation. As you can see in the last two equations, we derive the acceleration of the pendulum and the rotary arm equations. After linearizing and solving the accelerated terms, we derive the linear state space of the rotary inverted pendulum system. As you can see, these are the A and B matrices of the rotary inverted pendulum, which we later used to develop the LQR controller in order to perform linearized simulations. At first, we used a fully developed MATLAB workspace script as the system model algorithm. According to the fabricated physical system, we used all identified parameters to perform the linearized simulations to evaluate the system responses of the system for a given step input. Using the MATLAB Simulink, we implemented the full state feedback control loop as a linearized simulator, as you can see in the figure here. Using the defined LQR gain and parameter values from the system model script, we were able to derive all the linearized equations. In order to design the controller, first we developed a 3D CAD model of the rotary inverted pendulum system using SolidWorks. After importing the CAD model to the Simulink workspace using Simscape Multiple Link, we developed the controller. Here we used a classical controller PID. Here we actually used two PID controllers for the rotary arm and for the pendulum link, coupled them together as you can see here in the graph, and the sum was fed back to the system. Here we manually tuned the PID controllers to balance the system in a stable position. As you can see in the video, the rotary inverted pendulum system is performing under a steady state while rejecting external disturbances. As mentioned in the previous slide, we performed 3D simulations on a rotary inverted pendulum system using MATLAB Simulink software. To test the feasibility of performing the simulation experiments on a remote computer, we used video conferencing and remote controlling software, Zoom and AnyDesk. Using this software, we gave controlling access of the simulated model to a person using a different computer. Then we tested the simulation experiment whether we are getting the same results as when controlling it directly. Also, we tested this on a different computer laptop brands and we recorded the FPA rates on each computers. After configuring the nonlinear simulator using the defined LQR gain value, which showed it here, and setting up the initial condition of the rotary inverted pendulum system, we performed the simulation. As you can see, simulated result showed in the maximum control input as 2.2 volt and pendulum deflection is around 20 degrees. Especially, pendulum and the rotary arm have demonstrated a steady state response. Moreover, after tuning the LQR control Q and R weight matrices, the system reached its stability point in less than 3 seconds. Therefore, it's proven that it satisfies the natural frequency and the damping ratio in the developed control design according to the specifications. Talking about the nonlinear 3D simulation results, the system stabilized within just 4 seconds. As mentioned earlier, we used 2 coupled PID controllers in this module. The table here represents the control gain values of these 2 PID controllers. In these graphs, red line represents the behavior of the pendulum link and the blue represents the behavior of the rotary arm. Top 2 graphs represent the behavior of the rotary inverted pendulum system in a normal working environment, while the below 2 graphs represent the behavior of the rotary inverted pendulum system when an external disturbance is occurred. As you can see, the system is also perfectly capable of handling small external disturbances. In conclusion, in this research, we focused on 2 different objectives. First one is developing a software system that can replicate physical laboratory experiments. And we successfully achieved that using the MATLAB Simulink software. As the second objective, we wanted to test the feasibility of performing these simulation experiments on a remote computer setting so we can use this as a web-based teaching aid for distance learning purposes. We were able to successfully do that as well using some commonly used video conferencing and remote controlling software, Zoom and AnyDesk. As you can see in the below table, both of these softwares are capable of handling this and maintaining this in a very good FPS rate. Using this common software, not only students can perform mandatory lab experiments, they also can interact with other students and their lab instructors as well as their teachers. At the end of this experiment, we identified all the major hardware components needed during the development process and evaluated the technical specifications. For this pendulum system, we selected the 4-hub DC motor as the main actuator, and we selected the Texas Instrument C2000 development board for connecting to the Simulink in real time for parameter tuning and monitoring, while it being a very low-cost solution below $40 US. As for the future works, we are hoping to evaluate the real-time physical test bed and compare the results with the simulation model. After all the fabrication process, more advanced control approaches will be experimented and the comparison results will be performed. After the successful number of control design tryouts, the swing-up control for both simulation as well as for the real-time physical test bed will be performed. Lastly, it is proposed to develop a system where students can perform these laboratory experiments by interacting with physical system remotely. This will benefit a lot of students who don't have the access to such laboratory apparatuses in their university or in their country. Thank you very much.